I'd like to tell you a little bit about the history of knot theory. A lot of people talk about it, but nobody does anything about it. There's comments you'll find in, for example, the beginning of Rolfson's Knots and Links about something to do with Tate and smoke rings and so on, and vortex atom theory comes up. So I'd like to tell you where this all came about. Let me begin with just a slight philosophical comment. Poincaré addressed International Convention of Psychologists in 1908. He wanted to tell them about where ideas, creative ideas, come from. I don't know if any of you have ever read what he wrote, but the genesis of mathematical creation is a problem which intensely interests the psychologist. Poincaré was intensely interested because he had been noticing that if he worked really hard on a problem and had it in his head and then took a walk or relaxed, somehow his mind was still working. And he found that he often had very good ideas when he least expected it. In fact, once while he was stepping onto a tram, he had an idea that I think led to, well, I'm not absolutely sure exactly what the idea was. Groups or something. Is that right? Okay, yeah. And in fact, he thought to himself, I know this is right, I'll figure out the details tonight. And sometimes these ideas work, and sometimes they don't. And when they don't, what do mathematicians say? They say, well, too bad, it would have been beautiful. And Poincaré wanted to know how it was that our subconscious could be working while we're relaxing, with all these ideas bouncing around in our heads, all the possible combinations, and he of course knew very well how to compute the number of combinations possible. How could the mind pick out the useful ones, the good ones? And what he said was, the useful combinations are precisely the most beautiful combinations, and by those I mean the most able to charm the special sensibility that all mathematicians know, but of which the profane are so ignorant as to often be tempted to smile at. It is this special aesthetic sensibility which plays the role of a delicate sieve. In other words, the subconscious is looking around to see when a couple of ideas nicely complement each other, and then it raps on the subconscious and says, hey, wake up, think about this. This is his idea. I think psychologists still kind of laugh at this, but anyway, in some ways, knot theory began with two ideas coming together in the mind of one of the nuts. This talk is titled From Nuts to Knots, and the term nut is used in a non-rigorous psychological sense. So without further ado, here's our first nut. And these are old photos, and sometimes they're better than others, so some of them look a little funky just hanging there. This is William Thompson, also better known to us as Lord Kelvin. He was born in Ireland, and he was educated in Scotland. He was born in 1824. He lived a long time. He lived until 1907. He was a brilliant mathematician and physicist and an unreasonably confident man. You need to know this about him. As a Cambridge undergraduate, he was so sure that he was going to be senior wrangler. Now, this is the person who scores the highest on this grueling tripos exam. He was so sure he was going to be senior wrangler, he said to his servant, mind you, this is a quote from somebody who knew him, "Oh, just run down to the Senate House, will you, and see who is second wrangler." And the servant returned with a devastating answer, "You, sir." Thompson is really best known for this thing. Anybody know what it is? Cool answer. This is a device called a galvanometer, mirror galvanometer. It was an invention that he had to detect faint electrical signals from a telegraph wire that would stretch across the Atlantic Ocean. And the problem was that this was huge project was to get a transatlantic cable. And it took a lot of attempts because they usually broke. And he was on the ship for these attempts. But he had this idea of how do you detect this really, really faint electrical signal. And one day he noticed light reflecting off of his monocle. And that was the genesis for this idea, which made him very famous and very wealthy. So this is called the mirror galvanometer, and but he's really known to physics students for another reason. You know, the absolute temperature scale, Kelvin. Yeah, this is named after him, a byproduct of his important work on thermodynamics and heat. But there's something more important. There's the Kelvinator, which is the refrigerator that was made for many, many years, and I think the name might even still be around. I'm not sure. This was a lesser tribute. Anyway, after reading a book by Carnot, The Theory of the Power of Heat, Kelvin proposed a couple of laws expressing the indestructibility of energy. Now, it's interesting that a lot of famous scientists, not even famous, but a lot of scientists and mathematicians, the things that you learn early often become sort of the foundation for how you think about things later. Sometimes this becomes a help, sometimes this can become a hindrance. In his case, it became a bit of a hindrance because he believed that everything should be based on the primacy of the energy concept. And he had often formed these sweeping conclusions. In 1866, without any awareness of radioactivity, which was discovered later, he decided, well, you should be able to use the laws of thermodynamics to predict how old the Earth is. Because it just, you know, well, at some point they cooled down, so you just have to figure out how it's cooling. And he wrote a paper called On the Secular Cooling of the Earth. And in this paper, he rejected Maxwell's, excuse me, I'm sorry. In this, he rejected Darwin's ideas about evolution because he came up with a much smaller age for the Earth. And he just insisted that the geologists were wrong. It was so much the worse for them. And basically, Thompson was a creationist. And he also dismissed a lot of other ideas. There's a great biography of Thompson by David Lindley, who's a physicist. It's in print. It was only published about maybe 5 or 6 years ago. He says that Thompson became, he called him a living fossil, a holdover of a forgotten era. He rejected Maxwell's theory of electricity and magnetism. He rejected radioactivity. He insisted that the Earth was only 100 million years old, which was his dying day. Above all, he rejected the atomic theory. And just to give you an idea, here are some of his best pronouncements. X-rays will prove to be a hoax. So this is it. This is the, in some sense, the father of the nut theory. Okay. Here's our next nut. Again, term affectionately used. This is Peter Guthrie Tate. Tate was another Scottish student at Cambridge, and he was a senior wrangler. He was born in 1831, died in 1901. He was aggressive. I love the photo, so it tells you that. Argumentative, fiercely loyal to Thompson. We never agreed to differ, Thompson recalled after his lifelong friend and collaborator about his life had died. I think this was afterwards. He said, we always fought it out, but it was almost as great a pleasure to fight with Tate as it was to agree with him. I'm sorry. This is Thompson talking about Tate. So Tate joined the fray. He got into the age of the Earth controversy. And in 1885, he was still battling over this stuff. We cannot give more scope for geologist speculation than about 10 or say at most 15 billion years. So in 1860, when the University of Edinburgh was looking to fill a vacant chair of natural philosophy, one of the candidates was Maxwell, and Tate was the other. And they passed up Maxwell for Tate, partly because of his reputation as a teacher. And here's an interesting comment about Tate as a teacher. Never, I think, can there have been a more superb demonstrator. I had his burly figure before me, and the small twinkling eyes had a fascinating gleam in them. He could concentrate them until they held the object he looked at. When they flashed back around the room, he seemed to have drawn a rapier. I have seen a man fall back in alarm under Tate's arms.
Eyes.
Tate always said there were a dozen benches before him.
Is this an early teacher evaluation?
This is an early teacher evaluation. That's right. And he also said about Tate, however, that Tate's science weighed him to the earth. This is not a compliment. The author of these comments was Barry, who wrote Peter Pan. So this was the person who just heard a quote from. So Tate often played golf. You need to know this about him. He was crazy about golf. His son, Freddie Tate, was I think the best amateur golfer. I think they were only amateur golfers at the time. Best amateur golfer in Britain. Tate liked to play at 6:30 in the morning, and so he often played alone. And he recited Homer and Horace, the Greek writers, as he went along. He composed an ode entitled "The Morning Round," which he would sing when the classics weren't enough. It was based on a tune that you heard indirectly. It was called "Star of the Evening," and Lewis Carroll used it for his lobster quadrille. So it goes, beautiful round of golf, superbly played, round where never a mistake is made, who with enchantment would not bound for a round of the morning, beautiful round. Soup. So let's get on to his demonstration. In 1867, this is when, in some ways, the idea for knot theory began. Tate was showing Thompson how to make smoke rings do some tricks. And what he did was he took a big wooden box and he cut a round hole on one end, and he stretched a towel on the other end. And into the box, he put an acid and a base, which of course would combine and form vapor. What he used was a strong solution of ammonia and a dish that contained a common salt and sulfuric acid. And Tate explained later that two gases combine to form solid cell ammoniac, so that anything visible which escapes from the box is simply particles. So he knew these were particles of cell ammoniac. They're very, very small, and they remain suspended by fluid friction like smoke in the air. And when you rap on the back, you get this ring that would come out. If you look on my web page, there's a video. Susan's filming it, and the person who's helping me is the then chair of the chemistry department of the school down Dean Arts and Sciences. And he was afraid we were going to kill ourselves, so he wanted to be there. But he wound up, we had two of these boxes, and I made them look exactly according to the measurements. And we used the same reagents. We just wanted to see what would happen. You can use lots of other things to make the smoke rings. We wanted to get it as close as we could. It is beautiful how these things sail across the room very quietly and silently, but we could not make them do the tricks that Tate was doing. And he must have really practiced this thing. We couldn't make them collide. If you get one following another perfectly, the one that you're approaching will actually open up and allow the other one to go through, and then it will open up. And this one will speed through. It's because they're kind of twisting as they go through. They're going through the air, but there's a twist. And anyway, we know about this stuff from a book. This book that came out, Lectures in Recent Advances in Physical Science by Tate. This is a really neat book because he gave these lectures for some really friends who were non-scientific who wanted to know what had been going on in science. And so he arranged these lectures. And and he talked all through them, and somebody was supposed to have been taking notes. Somebody was supposed to have been taking notes. So instead, what happened was Tate found out that he was going to have to give the lectures all over again. And he did it again in his office with somebody transcribing it. And I think as a result, these things must sound exactly the way Tate did. And so they're fun to read. This book is rare, but it's not terribly valuable. You'll find copies of it even on the web. It's neat. So he pointed out that the room would have been pungent. Susan and I took several days to clear our lungs. This is really bad. But Tate also noticed that if you cut an elliptical hole or a square hole and you rap on it, what comes out is kind of misshapen, but it vibrates violently, and it settles down very quickly into a round shape. And he must have wondered about getting a knotted rings, but he sort of didn't say anything about it. And at the time, he was writing to Kelvin, and he wrote this rather cryptic thing. Have you ever tried plain air in one of your boxes? The effect is very surprising, but eschew NO5 and ZN. The true thing is, blah, 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 NH3. NO5 is dangerous, because put your head into a ring and feel the draft. Now, in 1840, dinitrogen pentoxide, N2O5, was discovered. And I'm guessing that that's what this was. And it should have been N2O5. But if you add water to this stuff, you get nitric acid. If you add ammonium salt, you get an explosion. He must have been really doing a lot with this. Anyway. So Kelvin was well aware of a lot of the Greek classics, and he was well aware of what Democritus wrote in ancient times. And I'm just quoting this: the principles of all things are the atoms and the void, and everything else exists only by convention. Nothing can come from non-being, and nothing could return by corruption to non-being. Atoms are unlimited in size and number, and they are the seat of vortex motion in the universe. In other words, atoms are universal, are eternal. Kelvin saw the smoke ring experiment, and he jumped to the conclusion that atoms must be microscopic knots of something called ether. At the time, everybody believed that there had to be something that you can't see in everywhere, permeating everything, called ether. Part of the reason was they wanted to explain action at a distance. How could the sun attract the earth and so forth if there was nothing there? So you have to imagine an odorless, frictionless, invisible substance. And now imagine that there are little knots of ether. This paper of Helmholtz that everybody had been reading at the time explained that if you had a perfect fluid like this, a knot created in it would actually never be destroyed. It would never cross itself. And that is a vortex, as they call it, a knotted vortex in ether, would be eternal. The only way you could get it there would be somehow to have created it at the moment you created the ether. This really appealed to Tate, who was not only versed in the classics, but also somewhat religious. I'd say probably very religious. That this sounded like the stamp of the creator. So knots were there because they were put there. The knotted bits of ether might give you different chemical elements. Well, sodium has two spectral lines, and people knew it at the time. And so Kelvin immediately jumped. Pardon me? Yes. Kelvin immediately jumped to the conclusion, those are the spectral lines of sodium, that must be Hopf. This was his guess. He went on to talk about all the possibilities that you could have. Every variety of combinations might exist. A long chain of vortex rings or 3 rings, each running through each other in the simplest fashion. One thing we really don't understand, this is completely gratuitous. One thing we don't understand is Kelvin was extremely enthusiastic, and his enthusiasm was infectious. And Tate was his great friend, and Tate was the one who showed the smoke ring experiment to Kelvin. But it took 9 years for Tate to kind of warm to this project. Maybe Tate had other things to do. But when he finally warmed to the idea of trying to classify knots, because you'd thereby be classifying the elements, he really threw himself into it. And this is the first paper that he wrote called On Knots. I just want you to see the title of it. And I also want you to see some of the work that he did. This is the first 7 orders of knottiness. Now you can't see it, but through the busting of this paper, you'll see no overcrossings and undercrossings. You see no way of whether it's this way or this way. And the reason is that at the time they believed that every knot could be drawn in such a way that all you have to do is go over, under, as you go around the body. Okay. So in every one of these pictures, you can imagine first going over, then going under, and so on. And of course, these are what we call alternating knots today. And it turned out this is not true, but you're okay.
So how good of a job did he do?
Okay, well, I'll come to it. He actually did a very good job. Now, also understand that he had no tools.
Right.
He had a magnificent intuition, and he worked like crazy. And so, after building a table of knots, these tables, by the way, this one here for seven crossings is essentially correct. I think it is correct. I'll say more about what he did later. After building a table for knots that could be drawn with 6 or fewer crossings, he was still dissatisfied because the enormous number of lines in the spectrum of elements suggested that you're going to need a lot of crossings, very complicated knots. So after doing this first 7 orders of knottiness, as he called it, even that was insufficient. 8 and higher numbers are not likely to be attacked by a rigorous process until the methods are immensely simplified, T. 77. In 1833, he wrote this: "We find that it becomes a mere question of skilled labor to draw all the possible knots having any number of crossings." That's quite an insult to the people who spent a lot of time trying to do this. The requisite labor increases with extreme rapidity as the number of crossings is increased. It is greatly to be desired that someone with the requisite leisure should try to extend this list. So Tate became a promoter, and he got other people to get involved in this. And one of the persons he got involved in this was Kirkman, who was a reverend. And this is Kirkman's definition of a knot. I've heard Scottish mathematician Laura Thistlethwaite read this definition with his accent, and it's wonderful. And I'm not even going to attempt it. I just want you to notice that it's what is a knot today. Well, for those of you who don't work with knots, take a cord, configure it any way you want, connect the ends. It's a circle. That's not a knot. That's a knot. And this is Kirkman's definition. Anyway, so what happened? Here's the deal. Kirkman sent Tate a redundant list of 166 10-crossing knots. Tate worked to weed out the duplications of 10-crossing knots. Yeah. Charles Little, this is a mathematician and civil engineer in Nebraska, then sent Tate a list of his own. And the two lists disagreed. Okay. Tate successfully located the single error before his publication. He had to go back to the galleys. He had to actually correct it because it was in the process of being published. In fact, there's 165, and 2 of them turned out to be the same. That was, as far as I know, the only thing wrong with this. And this is sometimes called the Perkoff error. It was not until 1974 that the 165 was the 165.
So even after they got up to 10, they still thought that every knot was alternating, and they just couldn't draw it?
Absolutely.
Okay.
Yes. So then, Kirkman sent Tate a list of 1,581 knots with 11 crossings, and Tate decided it was time to quit. All right, so now we come to my favorite knot. Now this isn't fair because he's a young kid at the time. This is James Clerk Maxwell, who grew up in a region of Scotland called Galway. His clothes were all handmade. This is a better picture later on. That's Maxwell and his wife, and down below is their dog Toby, who accompanied Maxwell everywhere at the Cavendish Knots. There are actually at least 2 Tobys. When one of them died, he was replaced by another one. Virtually identical, so it doesn't matter which one. It's a very spooky dog. The dog would lie underneath the lab bench where Maxwell was working and make strange noises when there were loud explosions and things. This is by description of one of Maxwell's biographers. And here's a later portrait. I'll explain what the connection is with Maxwell and Tate, all this stuff. Susan and I were in Edinburgh just a few years ago, and we were lucky enough to get an appointment with the people who run Maxwell's birthhouse, birthplace, which is now a small museum. This is where he was born, and Maxwell was a lifelong friend of Tate's. They knew each other in school, and they communicated by postcards that were very cryptic and very funny. At that time, you could send halfpenny postcards all across Britain, and because of the trains and because of British efficiency, sometimes these cards would actually arrive the day they were mailed, and it was not unheard of, although I find this really hard to believe, it was not unheard of to actually get a response back. But this is one of the cards that Maxwell sent to the paper. Can you read that first line? It's hard to read that.
Are you at home?
Right. You know, OT prime, are you at home? T prime is Tate. T being reserved for the grand man Thompson, or Tyndall. Anybody ever hear of John Tyndall? He was a popularizer of science at the time, and he's not highly respected by Maxwell and Tate, so they refer to him as T double prime and call him the second order quantity. This is instead they go on to say that next thing, that's spherical harmonics is the next term. And at the very bottom, you see. This is spherical something harmonics. Spherical harmonics. I'm trying to. It appears somewhere in here. But this is dPdt was how Maxwell signed all of his correspondence, and dPdt was a shorthand where dPdt equals James Clerk Maxwell, and this is one of the laws of thermodynamics: pressure, temperature. Joule's mechanical equivalent of heat, and so on. So, what we know is that Maxwell had been interested in Knox before Tate was, and this is a letter from 1867. If you have any spare copies of your translation of Helmholtz on board to us, that's the paper I mentioned where Helmholtz is talking about ideal fluids. I'll be obliged if you can send many launches into other work. And then now he's talking about warbles. Right, so you see a hop link here, and then you see this thing, which is a figure 8. And what Maxwell was really interested in was the Gauss linking integral. So Gauss had given a way of computing linking numbers of two things by doing a double integral. And Gauss seemed to have been interested in it for reasons of celestial mechanics. But when Maxwell looked at the integral, and this is actually one of the letters. When you look at the integral, when Maxwell looked at the integral, he realized that really what that integral was telling you was that if you ran an electric current through one knob, and got an induced magnetic field, and then along the other knob, you just thought of it as a path. Don't run current through it, but take a charged particle and go along that path. What you'd be computing, the work done by that particle against the field, would be a universal constant times the linking number. So this thing we just link like that would be linking number 1. And I won't go into a lot of details about that. But what really fascinated Maxwell was that you could have two curves here that one goes through one, but then goes back out the other way. And we measure that as 1 plus minus 1. If you go in this way, but later on you come back that way, you said to be doing zeroing. And yet, you can't pull them apart. That's what Maxwell was referring to by indivisible or warble. You can't pull them apart. And so, if you run current through one of those, and then run a particle around the other one, you do no work. And Maxwell thought this was incredible. And this page actually comes from his famous treatise on electricity and magnetism. It was the discovery by Gauss of this very integral expressing the work done on a magnetic pole. But it was Maxwell who realized that it was the work done. And then he goes on to say some other things, such as, but here's a picture of the simplest example of what I'm talking about. Two curves that, you know, the complicated one goes through one way and then comes out the other way. So that's another picture of what you just saw. And then Maxwell even considered what would happen if you did a whole weave of this thing going out to infinity. he has a lot of amazing things. Now, all of Maxwell's unpublished stuff has been published in a 2-volume set by Cambridge. They're large, expensive books, but they're amazing when they have them. And there's a fair bit of money there. Maxwell was so taken by this that this idea that two things could have zero linking, but could be kind of inseparable, that he expressed himself in the only way that he ever expressed himself when he was really feeling moved, and that was with bad verse. It's monstrous, horrid, shocking, beyond the power of thinking. Not to know interlocking is no mere form of linking. Interlocking means you can't pull it apart. We also had a chance to, I'll mention one other thing. This is Maxwell's stereo Wheel of Life, Lifezou Trunk. And if you look inside there, you will see a picture. It's a movie. You spin it and you watch one of the lenses. And you'll see 3 circles inside there. This was that's Maxwell's drawing in there. He was attempting to figure out what 3 smoke rings would do. I told you at the beginning what 2 smoke rings do. And one passes through the other. What would 3 do? You got 3, and one's catching up, and then the other's catching up, and they're going to do some kind of dance, as they move across the room. So he figured it out in mathematics. Once he'd solved it, then he drew the picture. And I've seen this picture. This is in the collected works. But Maxwell, by the way, also introduced the little lenses on here. This was his own introduction. And improved on what was a popular parlor toy. We'd heard about this, but we had a chance when we were in Cambridge the same summer to get a private tour of the artifacts of the Cavendish lab. They have a museum mostly of Maxwell. And this is Gordon Squires. He's a retired physics professor at Cambridge, who's now the curator. A curator who's more playful than careful with his objects. He's hauling, that is the device with the picture in it. He's gotten it out of the storage room. And this is a picture of us spinning it, having a great time. Maxwell also made Stereopticon images of knots. If you stare at that cross-eyed, you'll see a knot. It's quite amazing. But Maxwell, you know these Stereopticon viewers that were very popular in the Victoria days? Maxwell had his own device, and you read about it in his collected works. He had one lens, followed by 2 lenses. So you look at the one lens, and the object would hover in front of you. It's like, it's quite a different thing from looking through 2 small lenses with, at the image. You have one big lens, and then 2 small lenses, and then the card. And that was the thing I really wanted to see. And he knew we were coming. And he pulled it out, and that lens, that big lens that I'm looking through, that's where to put the head to get to see the image floating. That big lens had about 100 years of grime on it. And you notice he's got the cards kind of tacked on there with paper clips. I don't know if he's still curator. So, Maxwell had been studying knots before Tate, apparently. And this is a really fascinating letter. He's saying to Tate, there's a postcard, you're reading a paper in such and such a paper, Guthrie. The knots are in an older paper. He's referring to the work of Johann Benedict, who actually was writing about knots before Maxwell, or Maxwell was thinking about it earlier than Tate. And Tate apparently heard about Listing's work from Maxwell, but Tate was on the wrong thing. Listing you've probably never heard of, yet he's the person who invented the word topology. And in fact, he also invented some other words like micron. He's better known to ophthalmologists because he wrote a textbook on ophthalmology, physics of the eye. But what Tate was apparently reading, instead of the book on knots, was Sensus Ramesh Complex. Did I say that right? This is This is a book in which, published in 1862, in which Listing was attempting to understand the weather characteristic, vertices, lattices, spaces, two. Basically, he was trying to understand two. And he was starting to get onto the notion of bounded and unbounded regions, three-dimensional regions. And in this book, among other things, you will find that, which is a Mobius band. And this is the first published instance, the first publication of the Mobius band. It's before Mobius. It should probably be called the Gauss band because Mobius and Listing were both students of Gauss. It's likely that they learned about this from Gauss. But by the way, I'll just throw in a personal aside. This copy of Listing's book is something that I obtained from a book dealer many years ago, and it was given to Fuchs. And at the bottom of it it's inscribed to Fuchs. At the end of it, written in pencil, is Listing's comment that one should consider this perhaps for non-Euclidean spaces. Let's look at other characteristics of these issues of polyhedron non-Euclidean spaces. It's interesting that Listing was actually had an apartment next to Riemann's for a while, and there's a big question among historians as to how much communication they had. The fact that Riemann had tuberculosis maybe caused there to be some distance between the two. So what? Oh yeah, I guess. Thank you. Yeah, I missed it in the postcard to tape. You know, Maxwell said, "There's good stuff in that paper, but not nuts." And we think this is the absolute first instance of this bad pun. and Maxwell's not even content to write N-O-T, K-N-O-T-S. He has to take that and twist that even further. He had a sense of humor that always seemed to be racing ahead of his listener. There's a lot of people who've written about what it was like to talk to him, and it's very amusing. He had an incredibly good sense of humor. This is the book that Tate should have been reading, and this is the first instance of the word topology. And in this, you'll notice there's a nod here right in front of this. So, coming back to this whole business of Tate, after this business with knots, and after he'd done some classification with it, he published a book in it was around 1870. I think this is the second edition. Yeah, 1870, called The Unseen Universe: Physical Speculations on Future State. And there's a little trefoil at the top. Spiritualism was a big deal in Britain at the time, and a lot of other intelligent people were forming psychic societies, and behind all this was a huge desire to reconcile religion and science, and find a place for spirits to live. And gee, you know, if you could have a unseen dimension, you know, that's wonderful. Well, what Tate had done, what Tate had noticed was that there is no ether in this world that we can see. There's no perfect fluid. When he did the smoke ring experiment, he knew very well that this was not a perfect fluid. But what he decided, and when he wrote about the unseen universe, is that next to every particle of inferior ether, there's a particle of better ether. And next to the particle of better ether, there's a particle of even better ether. And so, all the way down. And so, in other words, he was imagining sort of a sequence of kind of parallel universes in which you, all your thoughts and all your actions vibrate to eternity. And he wrote this with Balfour Stewart, colleague, and the first several editions of this were anonymous. So you don't see his name on this at all. But the book was incredibly successful. It was written in a very hasty fashion, badly written, wildly successful. And one of the big critics of the book at the time was Clifford. Now, Clifford was an atheist, and an outspoken atheist. It was fine to be an atheist in Britain as long as you kept it to yourself. But if you were outspoken about it, we're going to tell you. And Clifford wrote this. Rather, let us contemplate the reposeful picture of the universal demand where these intelligent beings whiled away the tedium of eternity by blowing smoke rings from 63 kinds of mouths. And I love this last line, how fertile of resources the theologic mind when once it has Clifford's wheel. I kind of wonder if he was thinking about things like, so why does Clifford wind up in here as a nut? Let me tell you two things about Clifford. He lectured, he never missed his class for any reason, but one day he had to miss his class because he had a very important engagement. He was getting married. But he didn't tell his students. Instead, what he did was he put this on his door. And then we have this eyewitness account by a friend of his. His nerve at great heights was extraordinary. I am appalled now to think that he climbed up and sat on the crossbars of a weathercock in a church tower. And when, by the way of doing something worse than he was trying to do something better than his friend, and so he actually hung by his toes from the weathercock of the church. Hard to believe. And then his friend went up and did the same thing. I said, "What I'm appalled to think." So Maxwell, it's interesting. Maxwell didn't want to enter into this business about the unseen universe. Instead, Maxwell expressed his thoughts in a poem. And this poem has been quoted in various ways. When we were at the Maxwell House in Edinburgh, it sounds like a call. At the Maxwell House in Edinburgh, the curator opened up a closet and pulled out Tate's scrapbook, which had just been donated to, hadn't actually been seen by anybody in the public for probably over 100 years. It's written about it in Cargill Knox's biography of Tate, and he kept his scrapbook, but nobody had seen it. And Tate's great-grandson had just donated it. He was a very secretive person, didn't want anyone to listen about it. And they let us go through it, and I said, is there anything here original? Is there any letters perhaps from Maxwell? He said, no, nothing of that sort. And we opened it up, and there's a letter that's signed EPDT. And I asked her, could we photograph this? Oh yeah, photograph anything you want, but we have to close in 30 minutes. It's getting late. So.
And the notebooks and guns.
No pictures that big. But in it was the first version of this poem, which begins, my soul's an amplifier not, but actually in this version, entangled not. So, upon a liquid vortex wrought, by intellect in the unseen, this is reference to the unseen universe residing and not. And this is a very enigmatic poem. For all of its tools, for its untimed. By the way, this is a later version that you'll find, I think, on the web and in Cardinal Lott's book. When we looked at the original, we found there were many things that were different. Most interestingly is this word "its," I-T-S, in the original is Mayan time. Maxwell was dying when he wrote this poem. He was dying from a stomach cancer that had killed his mother at exactly the same age. And by this point, he knew that he was ill. But he was not really letting on much about it. And this poem is about a lot of things. It's about evolution. It's about it's about Darwin. It's about evolution. It's also about what we can know about the world. It's a little bit about what humans can possibly know. And I wrote an article about this that appeared in the notices at the AMS in November. So if you're interested in seeing the description of what this poem is about, have a look at that. this idea of extra dimensions was huge in England at the time. Of course, the book Platen came out in which this idea is explored in sort of a social satire way. But this is what let me mention with regard to this, Maxwell rejected the notion of 4 spatial dimensions, and he did it in a very funny way. He said, if there are 4 spatial dimensions and we live in 3, which 3? That strikes you as funny, but it's a reasonable question. This is what Maxwell finally had to say about the whole issue. Now, whatever may turn out to be the ultimate nature of the ether and the molecules, we know that to some extent, at least they obey some dynamic laws, and that they act upon one another in accordance with these laws. So therefore, it is absolutely disproved. It must remain the simplest and most probable assumption that they are finally made of the same stuff. That all material molecule is some kind of knot or coagulation. I think this is probably his last comment about it. Sometimes when I give this talk to people who don't know about Knox and where Knox sit today in science, let me just say that the vortex atom theory dissolved. No evidence was found for it. It was kind of quietly forgotten. Periodic table of elements came out not long after, and now this is kind of regarded as interesting historical stuff. But knots are found elsewhere, and they're found in DNA. They're found in fluid motion. They're found in solar flares. And there's so much activity in knot theory that 1992, a journal has actually begun dedicated to knot theory. And, so with that, I will stop. Thank you very much. No way I could have questions.
Do you think you can blow a knotted smoke ring?
Sorry?
Do you think you can blow a knotted smoke ring?
No.
So you agree that the
interesting
crossings
to try and invent something that would do it. Yeah. And can you even blow a linked one?
Has anyone else looked through this book, this giant?
That's a good question. I really would love to go back there and spend more time. There was only one page of knots in Tate's handwriting that we could find, and had some color in it. He seemed to be looking at live, and we photographed that. There were was there one other thing of Maxwell's in there? There was a lot of junk. There were also first drafts of articles that he had written, especially of book reviews. Oh, by the way, Tate wrote an obituary of Listing, on Listing. And one of the things Tate said was that Listing's book, since it's should be translated. No, then he said the only place you can see anything about it is in Maxwell's treatise. And Maxwell uses a lot of Listing's idea right at the beginning of his treatise. You can see the beginning of homology in here, because Maxwell needs the notion of a surface, homologous curves, and so on. And Tate says it really should be translated, and it has never been translated. The German is tough. The sentence, the words are almost as long as the sentence. They're pretty big. And it would be a neat thing to see the thing translated with some description, clarification. I think there was a book that came out recently in Princeton University Press. I forgot the author on Euler's formula. And there's several pages devoted to the census and listening to it. And, so there's a little bit more that's out there. But, much else. One thing I would like to understand though is why Maxwell went to the trouble of making these stereo images of knots. There's a sort of Maxwell scholar named Morris Eppa, PPLA, his first name, Morris. He's written some really masterful historical studies about Maxwell. And I asked him if he had any idea why Maxwell did this. Was he using it for his classes, or maybe he was exhibiting it elsewhere? Maxwell did go to meetings of the British Association, and he often had demonstrations there. At the Royal Institution, he projected the first color image using a color transparency, a three-color place of the same chart meridian. And this was so he liked to make models of things. He called them. He said they were for the sensible image worshippers. It's like anyway. So it's hard to believe he did all that for his own amusement.